Hey everyone, welcome back to Adherent Apologetics. As always, we are brought to you by you with your support on patreon.com/Adherent Apologetics. Today I'm here with Dr. Luke Barnes. He's a lecturer at West Sydney University with a Ph.D. in astronomy from the University of Cambridge. So sounds like a pretty smart guy. Dr. Barnes, welcome. How are you doing?
I'm doing very well, thanks. Thanks for having me.
Awesome. So just to start off, in case someone doesn't know who you are, could you talk a little bit about who you are and what you do?
So yeah, I'm a cosmologist and an astrophysicist. I live in Australia, so it's currently a very different time here than it is over there. I got my PhD from Cambridge in astronomy, and then worked in Switzerland for a bit, and I'm now back in Sydney, first as a postdoc and for postdoctoral researcher, and now as a lecturer at Western Sydney University. I've worked on a bunch of things. My main sort of scientific research area is galaxy formation, and particularly how we can simulate that in the computer. But I've also done work in this area of the fine tuning of the universe for life. So I've written some scientific papers on that, and a book with Geraint Lewis, a colleague and a friend of mine, who's also an atheist, incidentally, called A Fortunate Universe. We actually wrote our second book recently, which came out this year, just in time for us to not get out and do any talks to promote it at all. So let me just shamelessly plug it here. The Cosmic Revolutionaries Handbook. That one's about the evidence for the Big Bang, and particularly what you would need to do to overthrow the Big Bang if that's something you want to do. So even if you don't want to do that, it's a good nice tour through the universe. But that's so. A Fortunate Universe just sort of laid out this fine-tuning area, and then the last chapter is a Christian, myself, and Geraint, an atheist, just chatting about what we think all of this means.
So obviously it seems like as a cosmologist, you've done a lot of work, at least on the apologetic side of reality, especially with the fine-tuning argument. So what got you interested in studying fine-tuning, the fine-tuning argument, and how it relates to things like the existence of God?
So I sort of got into it by accident when I was in Cambridge. My PhD is actually in a much more technical area of galaxy formation, which I'm happy to explain for the next hour and a half if people are interested, as all people are about their PhDs who have one. As part of that, as a PhD student, we're encouraged to give a talk to the Wednesday night public observing nights that they put on at the observatory there. And I'd heard of this topic of the anthropic principle, fine-tuning, and so I thought I'll sign myself up to do a talk on that in a couple of months, and that'll motivate me to actually read all of this stuff. Because having done a PhD, I was sort of now in a position, well, being most of the way through a PhD, I was in a position to actually read the scientific literature itself, and evaluate good and bad on that. So I did the talk. As a part of that, I read a whole bunch of stuff in the scientific literature, good, solid science, just about what happens if you change these fundamental constants. But then there was a whole bunch of other stuff on the internet, and in some of the philosophical literature, and from Christians and from atheists, just that was terrible, just garbage. And so I started writing a set of posts for a blog that I was contributing to and still do, Letters to Nature, and just about just critiquing these articles. As a part of that, then one of the more famous critics of fine tuning, a physicist called Victor Stenger, Professor Stenger, put out a book called The Fallacy of Fine Tuning, and I started writing a reply to that. And as I was writing a reply, I realized he wasn't interacting with really any of the scientific literature. So what I needed to start by doing was to summarize the scientific literature on fine tuning, which I'd actually read. And I realized partway through this that I'd actually sort of written a review paper. Like I could publish this thing. And so I eventually did it. It came out in publications of the Astronomical Society of Australia. And then from that, once you've got into a field that deeply, you can start to see ways that it could be moved forward. So in particular, my work with cosmological simulations, we could use those to look more closely at these fine-tuning cases. And so applied for grants to the John Templeton Foundation and won those, and so did a couple of postdocs on pushing these sorts of ideas forwards with the tools that I have at hand as an astrophysicist. So that kind of along the way reconnected with Geraint, who was my honours supervisor before I went to Cambridge. Went back to Sydney University, where he is now, and was at the time, and started working on all this stuff with him, and along the way wrote a book with him.
Yeah, it's a lot of fun stuff there. I will encourage everyone at the end. We will be answering some questions. If you have questions or objections or things like that to the fine-tuning argument, we will hit some of those on the way out. But very briefly, if you could just kind of like present the fine-tuning argument, just kind of like walk through your formulation of it. I'd love for you to just kind of do that so that people can kind of have like an idea of where you're coming from with this argument.
Yeah, so I've actually written a paper for a philosophy journal called Ergo, and the paper's called A Reasonable Little Question. And then there's some subtitle that I wrote but have now forgotten. Something about a new formulation of the fine-tuning argument. So if people want to see all the technical detail, it's there. Roughly, I'm more and more seeing this argument as just kind of an extension of what might be called the design impression or the design intuition, that we look at nature and the whole thing looks sort of put together. It looks well assembled. We see things in nature that just sort of scream out that they've been thought through somehow. So you see a picture of my favorite example at the moment is just to show one of those slow motion videos of a hummingbird, super slow motion of it just hovering. It's astounding. I think one of the reasons why almost everyone throughout history and even today believes there's a God is this kind of intuition about the world that, not only where did all this stuff come from, but why is it such amazing, interconnected, complex, complicated, astounding stuff? But then as that's the design argument, that gets you about as far as, say, William Paley. It's about 1800. He's writing his book saying, look, if you walked across a heath, if you've got a heath near you, and you find a rock, there's a rock there. But if you find a watch, even if the watch doesn't work perfectly, you still think someone put this together because the bits, for various reasons, you then analyze your impression to try and work out what it is about the watch that gave you the impression that it's put together. And Paley's argument, it's sometimes presented as an argument from analogy, and I don't think that's quite fair. But basically, whatever leads you to conclude that the watch is designed, take that same intuition and look at nature, and it will look just as designed. But then Darwin comes along, middle of the 1800s, and the argument from his followers then, and I'm thinking here of particularly Richard Dawkins, but a whole load of people, is something along the lines of, look, we can explain where the processes that formed the complexity we see around us without actually having a divine hand just sort of pop in and actually arrange the atoms of a hummingbird into a hummingbird. So I think then this is where the fine-tuning argument comes in, because what that move is to say, okay, at the level of biology, so Dawkins has this quote that biology is the study of complicated things that have the appearance of being designed for a purpose. That's pretty much a quote if I've done that correctly. So that's basically saying, okay, biology looks designed, but if we go deeper, we'll find just the laws of physics. And if you're a biologist, those don't look obviously designed. But, we should actually look then at the law of physics. If that's your maneuver, okay, like biology is lost, that battlefield's gone. Let's look deeper and hope that the laws of physics don't look designed. Then now you're in the realm of fine-tuning. And in particular, one of the things that Dawkins says is one of the reasons we think that the natural world is designed, a way of fleshing out the intuition there, is to say, look, if I took all the stuff of a hummingbird, if I gave you 2 grams of matter, there you go. All right, do something interesting. Most of the ways to arrange that don't fly or reproduce or get nectar out of plants. So at the level of biology, we can think about rearranging cells, and most of the ways don't work. If we take that same intuition down to where we've been pointed by the Darwinists or whoever, the atheists. The question is, what happens if I just throw a universe together at random? Not just cells and just see what happens, but a universe together at random. And that's where fine-tuning comes in, because a way that we can attack that problem is to say, all right, there are these things in the ultimate laws of nature as we know them at the moment. I should say the deepest laws of nature, the fundamental laws, that so far as we know them at the moment, there are these numbers called the constants of nature, and they describe things like how heavy is an electron, various things about how the universe expands. What if we, in some way, throw those together at random in the way we were imagining throwing some cells together at random? And a good way of doing that, which is actually remarkably precise, again, go look up the technical details, is, all right, there's the laws that those numbers appear in, and we can there's a range of numbers that they could take in that law. Let's just change them across that range according to the ordinary sort of probability weightings that we have to do in physics anyway. And what happens, and we find that actually for most values of these constants, we get a dead, boring universe in which, again, nothing flies. Just like, most of the 2 grams of matter doesn't fly, most of the randomly thrown together universes don't have the ability to produce any kind of complexity at all. And we're talking things like no 2 particles stick together, or, the periodic table is gone. There is no way to make complexity. The whole universe ends in half a second. We're talking that sort of level of catastrophe. And so what that's showing is that your intuition of the design of the world, which almost everyone has, is completely intact at every level of science all the way down. And that's what I think the fine-tuning argument shows. It doesn't get overturned in physics. It's still there. We need a little bit more work to actually see it, to set up the experiment right, but it's still absolutely fine. And so the world looks like a well put together place right down to its fundamental laws.
So we'll go to some objections here in a little bit, but I think one of the things is what are some of these constants you're looking at in terms of the physics of it? You look at it and this seems to suggest fine tuning. Maybe you could give one or two or a few examples of those.
Right. So there are, depending on who you ask, about 30 of these constants, the fundamental constants. So if we follow the argument I was taking before, we're trying to get as deep as we can into the laws, while still holding on to laws that actually describe our universe. So we have at the moment what are called the standard models, the standard model of particle physics and the standard model of cosmology, describing how the smaller stuff is put together and how the overall expansion of the universe works. And between those two, there are about 30 constants, 30 numbers that we can't predict, we can measure, but we can't go into our equations and get them out of the equations. We have to put them into the equations. I think the best examples of fine-tuning, let me give sort of 2. One from cosmology, the overall structure of the universe, is there's a number in cosmology that's been around since Einstein first sort of put it in his equations in, I think, the 1920s. About the 1920s, called the cosmological constant. Now, when Einstein put it in, it was always sort of available in the equations, if you like, when he was reasoning from the principles he had towards the actual equations of gravity. This number could have been there. The simplest case would be that it's 0. In 1998, then jumping ahead in the story, we discovered that the number is not 0, or at least some form of matter that mimics the way that particular constant works is not 0. There's anyway, we won't get into too many details. Basically, there is such a thing as anti-gravity in the universe. There is something called either the cosmological constant or dark energy, which is whatever, either this constant or some form of energy out there, it's making the expansion of the universe accelerate. So a galaxy out there is moving away from us. We know that. It's moving faster today than it was yesterday. That's what we discovered. Within the equations, there's a range that this constant could have, And there are even reasons from fundamental physics to expect it to be somewhere sort of at random in that range. So its natural value is somewhere in randomly in that range. But if you want a life-permitting universe, if you want a universe that does something interesting, not just is there, it's a very, very narrow range around zero where this constant has to be. Relative to the total range, it's the fraction is something like 1 over and then a number with at least 90 digits, if not more. If you're outside that range, if you're negative, the universe just recollapses in about a second. If it's positive, the universe expands very fast, and outside of that range, too fast for anything to basically form. So you end up with just isolated particles in completely empty space. So the reason we know that there's no life in that universe, there's no complexity in that universe, is we know what's in that universe. There are isolated particles. It's a really easy universe to predict. And so that's a pretty solid case of fine-tuning. At the other end of the scale, we have things like how heavy is an electron, how heavy, the basic particles, right, of the universe. Here's the Lego pieces. How heavy are they? If you start messing with those for the basic particles that make up us, which are, for the record, the electron, the up quark, and the down quark, just for fun for everybody. Again, you end up with a very small range in which interesting things happen, like a periodic table. And outside that range, the particles basically don't stick to each other. More exactly, you can get quarks to stick to quarks, but then collections of quarks don't stick to collections of other quarks. So in our universe, the proton and the neutron are collections of quarks. Those sticking together make nuclei, which makes atoms, which makes chemistry, which is what you're made of, right? So we need that whole chain to work, right? From the quarks all the way up to you. With a very small tweak of these numbers, you get quarks put together into something, and then that's basically it. Those don't stick to each other. Your Lego set, you can't build more than 3 things, and that's basically the end of the story.
One more I'm curious about. I was talking with Dr. Alexander Proust, and one argument he found very powerful was the low entropy of the universe. So yeah. I'm curious, like what's going on there? Because I'm curious, because for something to be powerful to Dr. Alexander Proust, there's something going on here.
Yeah, so this is an interesting one. It's not one of the 31 constants, but I do a talk on this, and it takes like an hour to really nail this out. Here's my attempt at the short story. Yeah, here we go. Good luck, everyone. We see around us various processes that go in one direction in time and another. So if you get a glass and you fill it with ice and you just leave it in a room temperature room, and the ice will slowly melt into water, and then the water will come up to room temperature, and then nothing will happen for, put some Glad wrap over the top so it doesn't evaporate. But basically, if you leave that glass of water there, you can come back in a year, nothing ever happens. The reason why that's slightly weird is if you took that, to say you videotaped that for a year, right? If you then played that video in reverse, you would get almost a year worth of absolutely nothing happening. And then all of a sudden, the water in the glass starts ejecting heat into its environment, cooling down to the point where it forms ice cubes and then forms these cubes in the last, half an hour of the video, all of a sudden out of nowhere. The reason that's particularly weird is that when we look at the fundamental physics of what's going on here, of ice melting, of water changing temperature, there's nothing in the laws of physics themselves that gives us any direction of time. So to put that another way, we have these laws of nature, and one of the things you can imagine doing with a law of nature is you throw a scenario at it, and it will tell you whether that scenario could happen, whether that's consistent with the laws or whether it's not consistent with the laws, right? So throw a comet into the solar system and you want it to go around like this, and if it obeys the law, then that's the way it will go, the law of gravity. And if you want to do some weird path, then the law will tell you, no, that's not going to happen. If you obviously, the ice melting scenario is consistent with the laws. The weird thing is the ice spontaneously refreezing at room temperature. Let's hit reverse on that process. That one is also consistent with the laws, and yet no one's ever seen that in the history of the universe. You've never seen ice spontaneously melt at spontaneously refreeze at room temperature. Why is that? It's related, when we describe that, it's related to something called the second law of thermodynamics. That's how we sort of quantify which processes only go forwards in times versus which one actually do go forwards and backwards in time. So the question is, how do you put together these two ideas that there are so many processes around us, so many things around us which go in one direction of time and never in the other direction, versus the fundamental laws don't care which direction in time you're going? And as we've sort of put this together, the answer that's sort of the most common answer today, I think by far, and the most convincing answer, is that you have to have a very special beginning of the universe in the following specific sense. It must be the case that at the beginning of the universe, you had what's called low entropy, which is another way of saying is that the energy must be in a useful form. You can just define this in terms of how useful the energy is. So if I have a battery, it's very easy, if the battery's full, it's very easy for me to turn the chemical energy in the battery into electrical energy and then into, motion. If I put it in a fan or something, who knows? That's a useful form of energy. When the battery's dead, suppose I use the battery to run electricity to a fan, which turns the fan, and then it runs the battery dead. I've now got a dead battery, and the fan has moved the air around in the room and slightly heated it up a bit. So the energy that was now in here is now dispersed in the sort of slightly above where it was before temperature of the room. And that's a useless form of energy. The energy is still there. It's just almost impossible and basically practically impossible to turn that energy into another form of energy. I can't get it back in the battery, and I can't get it in any other form as well. I've just got a slightly hotter room. That's a way of seeing low entropy. So the start of our universe had loads of useful energy. We know what it would be like if a universe was born with no useful energy. It's a universe completely filled with black holes. Just won the Nobel Prize last night, by the way. If you didn't catch that, that was for the discovery of a black hole at the center of our solar system. Andrea Ghez, go look up what the stuff she's doing. It's amazing. And Roger Penrose, and Reinhardt, the other guy. Anyway,
I don't know.
Just edit that in, and I'll pretend I knew his name. So our universe has loads of useful energy at the beginning, and it's beyond plausibility, beyond belief that it was just a random fluctuation at the beginning of the universe for two reasons. The probability against it is just absurdly low. You get this number 10 to the 10 to the 123 that's actually Penrose is famous for. Now Nobel Prize winning Roger Penrose. And secondly, if you're waiting around for a fluctuation to give you the universe we see around us, there's less order in the universe today than there was in the past. And so if you want a random fluctuation to give the order we see, the cheapest thing to do, the easiest miracle, is to just get today rather than the past. And so the easiest way to make the universe today is not to make a consistent universe with a history where we have memories of a past that actually happened. It's actually just to create the universe as it is today with a whole bunch of false memories. Probabilities-wise, that's easier. So for all these sorts of reasons, yeah, we live in what seems like on face value, a very highly non-typical universe that has loads of free, useful energy at the beginning, so that there can be an arrow of time, and not again. There's a lot of chances for a universe to be completely boring, just black holes and nothing else happens. But that's not the way our universe turned out.
Well, I mean, fortunately, we do have a universe that's not just a bunch of black holes.
Yeah.
So thank you so much, Susan Lambo, for becoming a member and saying that we have the best guests on. I guess it's just because of Luke. So thank you so much for your support. Really appreciate becoming a member and supporting it here in Apologetics. So let's talk about some common objections. There's a lot of different areas we could go. So I kind of just put together some of like the most common things, maybe whether it's through online or versus like actual scholarship, because those things can be very different from time to time. But one of, I think, the most popular ideas is the multiverse. So I'm sure, like in almost any response to a fine-tuning argument, you're going to say, hey, a multiverse is possible, and eventually we're going to get a universe like ours that's exciting, and we have the chance for like intelligent life to develop. So like when you hear, but what about the multiverse? What's kind of like your response to that, Luke?
So I think when you set the argument up properly, the multiverse is actually irrelevant. So it's a perfectly fine, well, I was going to say it's a perfectly fine scientific idea, but that's up for grabs these days. Even if it was a perfectly fine scientific idea, let me start from the start. So the multiverse is the idea that basically, how do we get all the right conditions here? We basically won the cosmic lottery. There's loads of other places in the universe, and there's for some reason, every different area gets a different set of constants at random. So if you have enough bits of the universe and enough variation from place to place, then eventually somewhere we'll get the winning ticket. And so, or, a small number of places will get winning tickets. And we are one of those places. And obviously, there's no one in the losing places to sit there and go, "Oh man, this universe is terrible," right? There's no one there. So that's why we see a universe which has the right conditions for life. So I think if you set things up properly, that's fine. It's just not relevant. Remember we started off with our intuition, and then we went and looked at biology, and according to Dawkins, biology was lost. So we just tried to go as deep as we could go. If we really had a good multiverse theory, and what I mean there is, I'm a theoretical astrophysicist. I want some equations. I want to know what the initial conditions are, or whatever plays the role of initial conditions. I want to know what the constants are in those equations, if they have any, how they predict the multiverse, what the distribution is across the universe of these constants. I should say, changing the constants from place to place, I mentioned that before. That, for me, is the easiest way to imagine a multiverse. There are other ideas about disconnected bubbles, and maybe the differences were actually back in time rather than in different places. Anyway, it's a big sort of it's a big idea. If we had a proper multiverse theory, then that would become the new deepest level of physics that we would go and look at and ask our fine-tuning questions about, rather than asking them about things like the mass of the electron, which we think is a fundamental parameter, which is a fundamental parameter of the standard model of particle physics as we know it. We would now have a new and deeper theory in which the mass of the electron is not a fundamental constant, but is something dynamic, something that can change, something that could be different here as it is over there, and over there if you look far enough away. If we have a theory that it can actually do that, then we're at the next level down, and we start doing the whole fine-tuning thing again, because we're asking that question. The intuition we have about the well put togetherness of the world, does it survive all the way down? And so the problem with the multiverse is, it's not a question of whether a scientific explanation is successful. It's a question of whether the success of the theory makes our design intuition false. So if you see a hummingbird and you're amazed by a hummingbird, then if there's some process that built the hummingbird, so to speak, it seems likely on the face of things that would be an amazing process. It managed to build a hummingbird. And so you go down and look at the lower levels of chemistry and physics, and fine-tuning says, yeah, actually, the kind of universe that can build a hummingbird is an amazing universe. All right. If we had a multiverse, we'd just go down to that level and look at the multiverse and ask, does any old multiverse make a hummingbird? Or at least put us in a universe where we're likely to have a hummingbird rather than just be us boringly in empty space in a boring universe or something like that. And so the problem with the multiverse is we don't have a good enough theory to ask that deeper level question. We just don't have it. It's not, we can't go and get those equations and look at them and ask the question we want to ask. And so it's fine to sort of play around with these ideas, but they don't, in the absence of any reason to think that they're going to overturn fine-tuning, which gave us no reason to overturn what we saw in biology, which gave us no reason to overturn what we just saw in our, intuition, then the design intuition is fine. Like there's no, it's entirely possible, and given the state of physics, that a life-permitting multiverse is a rare and amazing thing. A hummingbird-producing multiverse seems like it might be an amazing thing. So having a successful explanation of the constants isn't the end of the story. The question is not whether we have a successful explanation, whether we have some sort of, boring, simple, natural, couldn't have been otherwise explanation of the constants.
Next objection we'll bring up, it was a live question, but we'll get to the other live question at the end, but we'll put this in now because it's a really common objection and a very interesting one to think about. And it's the idea of like appealing to brute facts. Like someone like Oppie would say that fine tuning is brute, but also asserts that it would be brute on theism because we can't know why God did it. What are Luke's thoughts? So there are a couple questions. One was like, what's your elevator pitch against brute facts? But like, what do you think about like fine tuning just being like some sort of brute fact?
I have to say I struggle to understand what Oppie's going on about. I'm an astronomer. There's no reason I would understand. I mean, he's a philosopher. It just seems to me. I don't know when you're allowed to make that maneuver. Here's the problem. If I understand what he's coming from correctly, and I need to go and read a bit more deeply, but it looks to me like under certain circumstances you can just take the way things are, and there's no deeper reason why they are the way things are. There's nothing like any sort of necessity there, and you're allowed to sort of wave your magic wand and say brute necessity or brute fact or whatever, and then as a result of that, the no further explanation of that thing is needed, or that explanation now no longer suffers from that fact no longer suffers from not having an explanation. It's fine with it. It's cool. When are you allowed to use that magic wand? I've never understood why on earth that would be the case. But to the second half of the question, yeah, so I guess if I tried to formalize that, my argument would be something along maybe like a reductio ad absurdum, or it proves too much or something like that. Like, unless you've got to give me some sort of account of when I'm allowed to use that magic wand. Otherwise, chaos ensues and anything gets explained, and we're all in deep trouble. I think he'd say something along the lines of, you're allowed to use it when there are other explanatory virtues to using it. And I think that might be enough just to open up the door for fine-tuning again. It just comes, but I'd have to look at that in a bit more detail. It would be brute on theism because we can't know why God did it. So I look at this in the paper I mentioned, A Reasonable Little Question. My answer to this is, ignoring ideas about brute necessity for the universe, if you just compare what the theist doesn't know is what God's intentions might be for a universe, and what the naturalist doesn't know at the level of, if we're just changing the fundamental laws, which constants might come up in the universe, if we're just considering things at that level. Those are not equivalent situations. I mean, what fine-tuning shows is that the kind of probabilities that get generated by not knowing the constants and having to guess them and then seeing if life turns out, the probabilities for that are, you know, one in numbers with 100 and the calculation I do in the paper gets about 130 digits or something. Whereas, what's the probability that God would want to create a universe in which there are embodied moral agents? Now, even if you say, I don't know, but, you know, 1 in a billion or something, you're still not in the ballpark of that. And it seems the only move you could make at that point is the one that actually Neil Manson tries to make in a recent paper of his, where he says that probability is simply inscrutable. We can't know what that is, and so the whole idea is shipwrecked. The problem with that for me is it seems like that's the equivalent of arguing, you know, we should reason as if the probability that God would create a life-permitting universe is 0, as if it's impossible. That seems way too strong. If you've got to assume that, then you're basically giving up the argument. I mean, one thing you could say here is that the fact that this argument appeals so naturally to so many theists, especially once they understand it, kind of suggests that actually the people who actually believe this theism thing don't have a problem with the probability that God would create a universe with moral agents in it. And so whatever that probability is, we don't need to know what it is. We don't have to be certain about what it is. We don't have to be any sort of, you know, sure about what it is. You could say 1 in a billion and the argument still goes through just fine.
We'll go to one more question here probably before we go to Q&A. There's a bunch of stuff, but a lot of times in the fine-tuning argument, you'll say, you know, there's a 1 in 10 to the 80th or 90th or 50th or 100th, you know, fill in the gap, power of this constant occurring. But when we look at these things, like as a cosmologist, like how do you generate the probabilities of like these things occurring? Like why isn't it like, let's say like a 20% chance or a 50% chance? Like how do we determine these probabilities?
Right. So that's a technical question. Again, I've got a paper and a previous paper actually on this, looking at fine probabilities within fine tuning. The short story is, as scientists, we propose a theory, which for us, you know, is a set of equations that the stuff of the universe is supposed to obey or be described by whatever theory of, whatever philosophy of physics you subscribe to. Inside those equations, there are free parameters. So the equation doesn't just predict everything. There are some numbers we have to put in. There's a bit of input, and then we get some output. Within the standard model of particle physics, for example, we have like the mass of the electron. Now, what do we do with the fact that we don't know what that number is, and the equation doesn't predict what that number is? Well, it means if you're considering the predictions of this model as a whole, you have to do what's called normalization, or sorry, not normalization. You always have to do normalization because it's a probability. Marginalization, that's the word I'm after. Got to get it right, otherwise someone will pull me up. You treat these parameters as what's called a nuisance parameter. So, I mean, the whole point of probability is that we don't know everything. So being unsure about something is kind of the whole point of the theory. So we can take into account in our predictions the statement, you know, I don't know what this number is, but it's in this range according to this equation. When we need to do that for everything. If you want to measure the mass of the electron, and you want to, at the end of the day, say something like, the probability that the mass of the electron is between here and here is 95%. If you want to make a statement like that, then you're going to need a probability distribution over the number before you saw the data. This is just the standard Bayesian thing. Go look up the equation in my paper. It's just absolutely standard. You got to have a prior. That's all we needed, right? If when the physicist uses that, when they wheel out that prior, which just is a mathematical statement of I proposed an equation. There was a free parameter in it, but I don't know what that parameter is. It's not anything like what it is for there's no deeper reason for what it is. So there's a range it could have. When we mathematize that statement, we get the probability we need then to go do fine tuning. So my claim is simply that we have these probabilities. They come out of physics. I don't have to sort of import them afresh.
We'll do one more quick question here, and then we'll go a little bit of Q&A. What about the idea that life just fit into the parameters of the universe? Probably one of the most common objections you'll see to the fine-tuning argument that, life just adapted to this universe, and to other universes it would adapt, and we'd still get life no matter what.
Yeah, it's false. There's not much to be said for it. Well, I had a friend who I was talking to about this. He's a biologist, and he immediately objected. Look, life is very robust. We've found life that can exist at 120 degrees Celsius, 20 degrees above boiling point, and it can exist at 20 degrees below boiling point, and it can exist in amazingly acidic environments and completely oxygen-free environments. And that's an extreme set of environments if you're a biologist. That is not an extreme set of environments if you're an astronomer. All right, those are some really cozy, nice and warm. If you're in those, you're fine. So most of space is basically a vacuum. The only thing there is the cosmic microwave background at 3 degrees above absolute zero. So minus 270 degrees, not minus 20 degrees. Occasionally there are clouds of stuff at 10 degrees above absolute zero. If you're inside a galaxy, then stars can heat up the interstellar stuff to 6,000 degrees. And so actually, minus 20 to 120 is not that bad. So the point is, when we as a physicist, when I declare, okay, that universe is done for, that one's toast, I'm doing it as we saw before, not on the basis of it's too hot or too acidic or something biological like that. It's things like that universe is going to end after half a second, and that one, no two protons will ever touch each other, and that one, nothing will stick to anything else. You won't even have a periodic table, and so we can keep things at that very broad conservative level without getting into too much detail. And on the basis of those, say that there are some very solid cases of fine-tuning even at that sort of level.
Let's go to a little bit of Q&A. We'll hit a few questions, and if anyone has anything else, we will try to fit it in. The first question here is a super chat from Fredo. Thank you so much for the super chat and the support. He says, if there's a brute fact on fine-tuning or leaning towards that, even as a possibility, what am I supposed to do with the brute fact that evolution is random? So he might be equivocating the fine-tuning argument here with evolution here. I'm not exactly sure what's going on. Do you kind of understand this?
I'm not entirely. Let me sort of answer the nearest question that I think this might be asking. I'm sorry if I've misunderstood it. Yeah. So I think when Oppie says fine-tuning is a brute fact, what he means is not really fine-tuning is a brute fact. That the state of our universe at the beginning could not have been otherwise, with all the constants and initial conditions there. That's the brute fact. And then the universe evolves from there. And I think he believes there's real chance in the universe, so that there could have been other ways. The universe could have been after that, but not at the beginning. So in that fact, that's what I think he means by fine-tuning. Then evolution is random. Let me just jump on that one quickly. I don't know what you mean by that, but if you read Dawkins or any good explainer of evolution, evolution is not random. It has a random component to it, but the whole point of natural selection is that it's not random. That's the whole point, right? It's not that you. So again, Dawkins, this is why he says that. Throw together 2 grams of matter, you won't make yourself a hummingbird. So it can't be a random process that put together all of this. That's the whole point of the book. It's that evolution is not a random process. So be careful of straw men.
Thank you for the question. And if you want to clarify it, feel free to put it in. The next question here is Ramon the Large. He says, what's your response to atheists saying all the dead failed solar systems? God bless. So I think he's obviously referring to, like, why is the rest of the universe like lifeless, it seems, if the universe is fine-tuned?
So I should say we have chapter 7 of my book with Geraint, which we wrote together. The bit where we split apart is chapter 8. It's just a response to a lot of these objections. I think we started A, B, C, and I think we got up to O before the end of the chapter. So this one's, it's a common one. If you can understand why life couldn't exist in a solar system which is dead or failed, then imagine a universe which is only dead and failed solar systems. And then you'll understand why there isn't life there. And then you'll understand why, our universe is interesting. It's no part of the claim of the fine-tuning argument that our universe, we would expect it to be completely full with life, cheek by jowl, as a wonderful book by John Leslie called Universes. We're just crammed in next to each other for the whole universe. And as I point out in the book, there is a reason for the empty space around us. It allows light to travel. So, for example, from the sun to us, we get the right amount of sunlight without being completely toasted or, too far away. And it allows the Earth to move freely around the sun to keep that constant speed. If the whole solar system was full of air at a breathable density, like in this room, even if it was stable, the Earth, because of the drag going through all the air, would basically spiral into the sun in about a month. So, there's a reason for the empty space, and having so much of it out there just gives us a beautiful night sky. What are you whinging about?
Awesome. Thank you. Another question here from the programmer. It says, Dr. Martin Rees says the existence of the universe is just dumb luck since we wouldn't have existed anyways. What are your thoughts?
Oh, that is not my memory of what Martin Rees says at all. He's a fan of the multiverse. So I have met Martin Rees. He was at Cambridge when I was there. I've met him since. As I've chatted to him, no, he's a fan of them. He's read his papers, read his book, Just Six Numbers, wonderful book. So he's a fan of the multiverse. He's not on the camp of if things hadn't been just right for life, then we wouldn't have existed. So how can we be surprised that there's the conditions for life? That's sort of the anthropic objection that basically no scientist uses that objection. A very small number of philosophers have tried it, but no, that's not the answer that's ever put forward in the scientific literature for fine-tuning. So that's not what Rees says. No, he's a multiverse advocate.
Might be a clarification here on the question. It says it's a matter of possibilities clearly proved otherwise. So a multiverse allows evolution in its possibilities, that it can't be random if not the following constants in the multiverse and evolution's false. Don't know if you're picking up anything here.
That hasn't really helped. It's a matter of possibilities clearly proved otherwise. So a multiverse allows evolution in its possibilities that can't be random. If not following constants. So let me just answer what might be the right question. Mm-hmm. To have something worthy of being called a multiverse, yes, there has to be some way in which what we think of as a constant, the mass of the electron, is different here from what it is, over there somewhere. Mm-hmm. It has to be random. It'd be random in the sense that if it was just, if it was designed, then it wouldn't really avoid the design argument. And there's not really much chance for any sort of, natural selection of universes, to put it that way. Mm-hmm. So the multiverse allows evolution in its possibilities. Well, it it must create different regions of constants. But then what we think of as constants aren't constants, but there might be a deeper level of constants. You've written down a new theory, which I'd love to see if anyone's got one. And you've written down this deeper theory. What are its constants, and what happens if I change those constants? Those are the questions we want to
ask. One more question here from Andres Ekren. It says, if there was empirical evidence of an infinite number of universes, how would that impact the fine-tuning argument?
Well, it's hard to imagine how you could get empirical evidence of an infinite number of universes. The important thing for me in any multiverse scenario is that you have to... So we have the standard model of particle physics. In that model, the mass of the electron is a constant that you put in, right? Modulo some stuff about renormalization in quantum field theory. Sort that out yourself. It's a constant we have to put in. If you're going to make a multiverse in which the constant here and over there are different, we need a new set of equations. Okay. So the important thing is, can you write down a set of equations that does that creates the multiverse we need, and we have some reason to think that that equation actually describes the universe around us. There's some way that we could get some sort of empirical evidence, because we're doing science, to actually know whether that equation, rather than any other equation, is a useful description, and a useful, deeper description than the laws. Once we've got that, if you've got that, then we've got a deeper level in the argument we can go look at, and we can do the next step of the argument. In the absence of that, you're just sort of, punting to ignorance. Maybe what we don't know will completely override what we do know. I mean, this is why Dawkins sort of kicks the ball from biology into physics, in the hope that physics, that looks simple enough, and it won't be too complicated in design. Look, and then fine-tuning says, no, it is, sorry. And so you just then kick the ball further out into the multiverse where we can't see it anymore. So do some more physics, and then we can look at the argument again.
Awesome. Thank you so much for your time, Luke. A lot of ground we covered. 50 minutes has flown by. Is there any kind of last thoughts, things we didn't touch on that you want to bring up before we wrap things up here?
There's one I get quite a bit, which I should just jump. There's the objection. There's no reason to. How do you know that these other constants are even possible? I get this one all the time, and immediately, this is a bit like the Oppie's magic wand. That's a bit pejorative, isn't it? But anyway, when are you allowed to just declare that something is impossible? And it seems to me, if you're going to declare something impossible, not just not actual, I mean, there's a difference between saying there's no such thing as fairies and there couldn't possibly be any such thing as fairies. Those are two really, really different statements. If you say there's no such thing as fairies, what you mean is, look, we have video cameras and stuff. We'd have spotted fairies. If there were fairies, we'd have spotted them by now. Versus saying there could not possibly be any such thing as fairies. Well, if you're going to say that, you don't need video cameras. You better produce some sort of argument to say that there's something internally inconsistent about the idea of fairies. Like, why is it impossible for fairies to exist, or unicorns, or whatever? And so if you want to say, look, in fine-tuning, I have a set of equations that is the best description we have of the universe in front of us. In that equation, there are free parameters, and I can change those parameters without in any way affecting the mathematical consistency of the description. Right? Everything mathematically is fine. Mathematics gives, change the number a bit, big tick, which is why we have to go and measure it. You can't just sit on your, in your armchair and say, I'll have, I reckon the number has to be over here. If you want to then say, okay, you have a completely self-consistent, mathematically consistent description of a universe which has the same fundamental laws as ours, but just a slightly heavier electron, I'm going to say that universe is completely impossible. It couldn't possibly exist. Why? for Pete's sake, what's missing in that explanation is the explanation. Why? Give us a reason. And if you've got a reason, that could be really interesting. It could be the kind of thing that lets us, derive the value of the electron mass. You could go to Stockholm and get your own Nobel Prize for that, right? Tell us. So just throwing out, again, it's this magic wand of necessity. I can just say that these constants are necessary, and then I don't have to worry about it at all. Yeah. So I think you're just writing yourself a plan. You're writing yourself a check that you need to cash. You need to give us some reason why they have to be this way rather than another way. Because I think the default assumption is that if you have a consistent description of the way the world could have been, then that's a possible way the world could have been. Unless you've got some very high-powered metaphysics, in which case, be my guest, do that as well, and we'll see what happens.
Yeah, well, there's so much great stuff you brought in here in this hour, Luke. Really appreciate your time as always. There's a link down below for you to follow Luke on his work. There's lots of great stuff coming. Can't wait to see what's next. And if you're new to Adherent Apologetics, there's the book there's there.
The book.
There's the
Shameless.
book.
The Cosmic Revolutionary's Handbook.
There we go. I encourage everyone to check out that book, and I will add a link to that book in the description if you're watching late. This is Adherent Apologetics as always. I encourage everyone, if you're new here, subscribe, leave a like if you're listening via YouTube, and leave a rating over on the podcast. Really appreciate it. And if you enjoy the show, you can support the show, patreon.com/Adherent Apologetics, or becoming a member. Big thank you to Susan for that, and everyone who supported and tuned in today. Luke, thank you so much for your time. I really appreciate it.